What if I told you that right now, there's an object so powerful that it can bend space itself, slow down time, and trap light forever? What if I told you that these cosmic monsters are hiding throughout our galaxy, and one supermassive giant sits at the very heart of the Milky Way? Today, we're diving deep into one of the universe's most mind-bending phenomena: black holes. By the end of this video, you'll understand not just what they are, but how they completely break our everyday understanding of reality. Let's start with the basics. A black hole isn't actually a hole at all. It's an incredibly dense object with gravitational pull, so strong that nothing, not even light, can escape once it gets too close. Imagine trying to throw a baseball so hard that it never comes back down to Earth. You'd need to throw it at about 25,000 miles per hour. That's called escape velocity. Now imagine an object so dense that its escape velocity is faster than the speed of light. Since nothing can travel faster than light, nothing can escape. That's a black hole. But here's where it gets weird. The blackness isn't the object itself. It's the region around it, called the event horizon. Think of it as a point of no return. Cross that invisible boundary, and you're gone forever, swallowed by space-time itself. The actual stuff of the black hole, what physicists call a singularity, is theoretically a point of infinite density at the center. But honestly, we don't really know what happens there, because our physics breaks down completely. Most black holes form when massive stars die spectacular deaths. Picture a star at least 25 times heavier than our sun. For millions of years, it's been in a constant battle. Gravity trying to crush it inward, nuclear fusion pushing outward. Eventually, the star runs out of fuel. Without that outward pressure, gravity wins catastrophically. The star's core collapses in less than a second, crushing matter so violently that protons and electrons are mashed together into neutrons. If the core is heavy enough, even neutron pressure can't stop the collapse. The result? A supernova explosion that can be seen from billions of light years away, leaving behind a black hole where a star once shone. But that's just one type: supermassive black holes, millions or billions of times heavier than our sun. Probably formed in the early universe through different processes we're still figuring out. Some might have grown from smaller seed black holes, others might have collapsed directly from massive gas clouds. Here's where black holes get truly mind-bending. Einstein showed us that massive objects don't just attract things with gravity, they actually warp the fabric of space-time itself. Imagine stretching out a rubber sheet and placing a bowling ball in the middle. The sheet curves around the ball, now roll a marble nearby. It doesn't travel in a straight line anymore, it curves around the depression. That's essentially how gravity works. Black holes create such an extreme warp in space-time that they create what's called a gravity well, so deep that even light gets trapped. But the effects extend far beyond the event horizon. As you approach a black hole, time literally slows down relative to someone watching from far away. This isn't science fiction, it's measurable reality called gravitational time dilation. An astronaut falling toward a black hole would appear to slow down and freeze at the event horizon to an outside observer while experiencing normal time themselves. Even more bizarre, if you were falling feet first toward a black hole, the gravity at your feet would be stronger than at your head, stretching you vertically in a process physicists cheerfully call spaghettification. Stephen Hawking discovered something shocking. Black holes aren't perfectly black. They actually emit radiation and slowly evaporate over time. Here's how it works. Even in empty space, quantum mechanics tells us that particle-antiparticle pairs are constantly popping into existence and annihilating each other. Usually, we can't detect this because they cancel out instantly. But near a black hole's event horizon, something strange happens. Sometimes one particle from a pair falls into the black hole while its partner escapes. The escaping particle becomes real radiation that we can detect, while the black hole loses a tiny bit of mass energy. This means black holes are slowly shrinking. But here's the kicker. Smaller black holes evaporate faster than large ones. A black hole with the mass of our sun would take longer than the age of the universe to evaporate completely. But a black hole the size of a mountain would disappear in less than a second, releasing more energy than the world's largest nuclear bombs. The final moments of a black hole's life would be an incredibly violent explosion, as it rapidly evaporates away the last of its mass. Nobody knows what actually happens inside a black hole, because no information can escape to tell us. But physicists have some wild theories. At the center is the singularity, a point where density becomes infinite and space-time curves infinitely. Our current physics can't describe what happens there. Some theories suggest the singularity isn't real, but represents the limit of our understanding. Other theories propose that black holes might be gateways to other parts of the universe, or even other universes entirely. Some physicists think they might be firewalls that incinerate anything crossing the event horizon. Others believe they're more like holographic information storage systems. The truth is, we need a theory of quantum gravity, combining Einstein's relativity with quantum mechanics to really understand what's going on inside. Until then, black hole interiors remain one of physics' greatest mysteries. Black holes aren't just theoretical curiosities, they're everywhere in our universe and play crucial roles in cosmic evolution. Our own galaxy, the Milky Way, has a supermassive black hole called Sagittarius A at its center, weighing about 4 million times more than our Sun. In 2022, scientists captured the first direct image of it using a global network of radio telescopes. These supermassive black holes seem to regulate galaxy formation, controlling how fast stars can form by heating up surrounding gas with powerful jets of particles traveling near light speed. Stellar mass black holes are probably scattered throughout the galaxy. Scientists estimate there might be 100 million of them in the Milky Way alone. Most are invisible, detectable only when they steal material from nearby companion stars. When black holes collide, they create ripples in space-time called gravitational waves. In 2015, scientists detected these waves for the first time, opening an entirely new way to study the universe. Black hole research is exploding right now. The Event Horizon Telescope gave us our first direct images of black holes. First M87 in 2019, then Sagittarius A in 2022. These images confirmed decades of theoretical predictions about how black holes should look. Gravitational wave detectors are discovering black hole mergers regularly, revealing that these cosmic collisions are far more common than we expected. We've learned about black holes with unexpected masses and spins that are forcing us to revise our theories. Scientists are working on next-generation telescopes that might detect the shadows of smaller black holes, and space-based gravitational wave detectors that could observe black hole mergers throughout cosmic history. Some researchers are even working on laboratory experiments to create artificial event horizons using sound waves or light, testing Hawking radiation in controlled conditions. Black holes represent the ultimate intersection of the very large and the very small, where Einstein's gravity meets quantum mechanics in ways we're still trying to understand. They're cosmic laboratories for testing the most extreme physics imaginable, time machines that let us study the universe's history, and possibly gateways to understanding the deepest nature of reality itself. What started as a mathematical curiosity in Einstein's equations has become central to our understanding of how galaxies form, how space-time behaves, and what happens when physics reaches its limits. The universe is far stranger than we imagine, and black holes remind us that we're still uncovering its deepest secrets. What's the most mind-bending thing about black holes to you? Let me know in the comments, and don't forget to subscribe for more cosmic deep dives.